Welcome back. This is tutorial 4B Laplace transform, where we are answering question 3. We are given ys, the Laplace transform of yt, and we are asked to find yt in this question. So this is a question of inverse Laplace transform. We are told that ys equals to hs xs, and this is hs, and this is x of s. So how to find yt? Here the answer gives us more information about xt. If xs equals to 1 over s plus 3, then its inverse Laplace transform is e minus 3t. But we don't need to do that because we can actually begin from y of s directly. When we have y of s in this form, the question really is how to find it in a simpler form such that we can find this expression in the lookup table for each of these value. This part is very simple. Once we have found k3, then the answer, the inverse Laplace transform, is simply k3 e minus 3t. This is a more difficult expression to find the equivalent in time domain. So in time domain, once you have seen the denominator with complex conjugate pairs, you'll realize that in here there will be a cosine or a sine term. The values, of course, then depend on k1 and k2, which will tell us the magnitude and phase of the expression. Typically, I'm going to ask you to use the cosine expression and then find the magnitude and phase. So the question now is, which one do we identify with to make our computation easier? Let us go and plot the poles and 0 of k1 over s plus 1 plus j2 and k2 s plus 1 minus j2. So the pole here is at minus 1 minus j2. And the pole over here, the second one, is at minus 1 plus j2. So this is the expression with respect to k2, and this is with respect to k1. Minus 1 is sitting on the real line at the negative side, and plus j2, which is on the plane on top, where this is minus j2. I'm going to ask you to remember that when you identify a complex conjugate pair, always look at the positive j2 expression with k2. Alright. Let's assume that you can do the partial fraction expansion from here to here. This is highly mechanical, and these computations are expressed here. So we have k3, and the answer of k3 is minus 1. k1 is this value here, and therefore k2 would be, actually, if this is k1, then k2 would be 0.559 angle minus 26.6, because k1 and k2 are complex conjugate of each other as well. So in the lectures, you'll realize that once you have identified the numerators associated with the pole at the positive j-axis, then these values becomes important. So these values are substituted here in the cosine. So minus 26.6 is from here. 0.559 is actually this value, 2 times 0.559. And what about cosine 2t? Where did that come from? So the 2 came from here, it is the minus 1 plus J2, and this is the position of the omega naught at J2, positive J2. So that's why it is positive 2 here. And then what about this value of minus 1? This is sigma equals to minus 1. It is here, the minus 1 over here. So this is the 4 values that we need to extract from the complex conjugate pair, which is the K1, that is a magnitude and a phase, K2 and magnitude and the phase, as well as the sigma and the omega. These 4 values are the important value. So don't confuse yourself. Always find the value that is with respect to the positive omega, because in the K1 and K2, one of them will be the complex conjugate of each other. So this is the minus theta over here, and this is the positive theta. But because we know which one to take, if you take the wrong one, then the phase will be wrong, will be a net conjugate of it. So we have identified that this is minus 1 plus J2. So this is the positive frequency. We will take the corresponding value of phase here to substitute into this expression on the right hand side. Now, so in this question, actually if you are given K1, K2 and K3, then finding this expression is trivial. However, trying to do the partial fraction expansion is non-trivial. If you are in the lab, I would advise you to use MATLAB to do this, where we use the residual to find the RPKs. So this is the RPKs, which immediately give us the expression of partial fraction expansion from the coefficients given in the N and D1 and D2. This you have to try in the lab as well as at home to verify that my answer is correct. So with that, we have found what is YT. You can also use the inverse Laplace of MATLAB to verify your answer. Let us now verify using MATLAB. We enter the expression of ys and use inverse Laplace ys to get yt. The answer is this. And if you compare this against this, it does not look the same. Well, it looks the same here, but it does not look the same for 1.118 times e minus t cosine 2t minus 26.6. So where's the difference? Well, let's find the similarity first. E minus t we have here, and then the difference is that we have it as magnitude and phase shift, while here we have sum of cosines and sines. So let us remind ourselves that actually we can express 1.118, this expression over here, e minus t cosine 2t minus 26.6, as sum of sine and cosine. So let us see why. Remember that if we have cosine bracket a minus b, and then by the trigonometric identity, the sum of angle formula, cosine bracket a minus b is cosine a cosine b plus sine a sine b. So if we use a as 2t and b as theta, then we are only needing to solve for what is k and theta, or a and b. In this case, we have k, which is 1.118, and theta, which is minus 26.6. Therefore, we can find a and b. Or in our example, our value is 1 and half for cosine B and cosine B, this one, and this guy is sine B, and therefore we can find K and theta. So K cos theta, or I should say K cos B equals to 1, K sine B equals to half, and then when we substitute it, we get the expression of it as magnitude of 1.118 and phase of minus 26.6. Remember that in our calculation, we are doing it in radians, so this is not typical. We never want to write it in degree. In the book, it was written in degree, so I follow suit. So the take-home message is that when you use the inverse Laplace transform of MATLAB, you get an expression as sum of cosines and sine instead of magnitude and phase, and sometimes you're asked to convert this expression into magnitude and phase. In the last part, we are asked to find the initial and the final value. One way, of course, is that we will plot the signal, and then in the initial value, we can read it at time 0, which is 0 value, and when it goes to infinity, it is also 0. So we are just plotting and we are verifying. Now we use the initial and final value theorem. So what do? We take y of s, we multiply s with y of s, and let s tends to infinity. So s multiplied by this whole expression over here and set s to infinity. So we come out with this expression on the bottom, and then because the numerator and the denominator have s squared, and because we want s to goes to infinity, we multiply both sides by 1 over s squared. When we do that, this is 1. So what we have is 1 over s squared, 3s squared will become 1, s over s squared will become 1 over s. That's the numerator. And the denominator will be s squared times 1 over s squared will become 1, 2 over s plus 5 over s squared times 1 over s plus 3. We let s tends to infinity. This will become 1 plus 0. This guy goes to 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 infinity. So it is 1 over infinity is equals to 0. So using the initial value theorem, it works. What about using the final value theorem? Using the final value theorem, we have the same expression s times fs, but this time we let s to be 0. So we start from this point. We use this expression which we have calculated, and now we let s tends to 0. When s less than tends to 0, this is easy. Simply this is 0, this is 0, 0, 0, 0, 0. Multiply by s, which tends to 0, and therefore the total answer is 0. So I should put the s here. So again, I repeat, the numerator goes to 0 times anything on the right hand side. Since the numerator is equal to 0, the whole expression goes to 0. So the final value theorem tells us that y infinity is 0, and this agrees with our plot. Thank you.